All right, welcome to the Explainer. If you've ever had to deal with data, you know it can get, well, messy, super messy. So today we're going to tackle that head on. We're going to learn the art of database normalization, which is basically a fancy way of saying we're going to turn total data chaos into something clean, efficient, and totally reliable.
So here's the game plan. First, we'll dig into why messy data is such a huge problem. Then, we're going to level up through the different normal forms. Yeah, you can totally think of them like levels in a game. And at the end, we'll talk about the big payoff, why going through all this is absolutely worth your time. Okay, let's dive right in. To really get why normalization is so cool, you first have to see just how bad things can get without it. Let's take a look at why even a super simple table can be a total trap.
So, you look at this table, right? Seems totally fine. We've got employees, their ratings, how much they make, the hours they worked. Simple. But trust me, hiding right under the surface, this innocent-looking design is basically a minefield just waiting to blow up your data.
These hidden dangers have a name: anomalies. Let me walk you through them. First, you've got the update anomaly. Let's say we need to give everyone with a rating of 8 a raise. Well, you have to go and change 3 different rows. What if you miss one? Boom, your data is instantly inconsistent. Then there's the insertion anomaly. What if you want to create a new pay grade? Say a rating of 12 pays $15 an hour, but you haven't hired anyone for that role yet? You can't. There's nowhere to put that information. And maybe the scariest is the deletion anomaly. See Smith there? He's our only employee with a rating of 10. If we delete his record, the fact that a rating of 10 corresponds to $12 an hour just vanishes, gone forever. This is exactly why this setup is so fragile.
So, how do we fix this mess? Well, our first step toward a healthy database is what we call first normal form, or 1NF for short. Think of this as rule number 1, the absolute ground floor for any decent relational database.
And the rule for 1NF is super simple. Every single cell can only hold one single value. It has to be atomic. That means no lists, no jamming multiple phone numbers into one field with commas, just one value per cell. Now, our example table, it actually passes this test, so it's already in 1NF. But we're just getting started. The real issues are hiding a lot deeper.
All right, now we're getting to the real heart of it. To fix those anomalies we talked about, we need to understand the hidden rules inside our data. These are called dependencies, and they're basically our secret map for how to strategically break this one big clunky table into smaller, much cleaner ones. This idea of a functional dependency is literally the engine that drives this whole process. It's a really simple concept. If you know X, you can figure out Y. Every time. For example, if you know an employee's social security number, you know their name. The SSN determines the name. And we're about to use these powerful little rules to take our messy table apart piece by piece. Okay, next level, second normal form, or 2NF. This one is all about getting rid of something called partial dependencies. Now hang with me here. To get this, you need a primary key, which is just what uniquely identifies a row. Let's pretend for a second that our primary key is both the SSN and the hours worked combined. See the problem? The employee's name and their rating, they only depend on the SSN part of that key. They have nothing to do with the hours worked. That's a partial dependency. And that's exactly what's causing our update problems. So, what's the fix? You guessed it. We split the table, pulling out everything that depends only on the SSN into its own separate space.
Moving on up to third normal form, or 3NF. This level tackles transitive dependencies. Just look at the chain here. The SSN determines the rating, and the rating determines the hourly wages. So the wage doesn't depend directly on the employee, it depends on a non-key attribute, the rating. It's like a game of telephone. This indirect relationship is what's causing those insertion and deletion anomalies. So 3NF tells us, break that chain. We're going to pull the rating and the wage out into their very own table.
And look at that. Here's the beautiful result. We've taken that one big, problem-filled table and turned it into 3 small, super-focused tables. We've got one for employees, one for wages, and one for the hours they work. Now, if you want to change the wage for a rating of 8, you change it in exactly one place. That's it. The anomalies, gone. Our data is finally clean and trustworthy. Now, for most situations, honestly, 3NF is where you can stop. It's kind of the gold standard. But if you're a perfectionist, if you want the absolute highest level of data purity, there's an even stricter level, Boyce-Codd normal form, or BCNF. So what's the big difference here? Well, you can think of BCNF as a super strict version of 3NF. It boils everything down to one simple, powerful rule.
Anytime you have a dependency where A determines B, that A has to be a superkey, meaning it has to be a unique identifier for a row. No ifs, ands, or buts. This just cleans up a few really obscure edge cases that 3NF might occasionally let slide.
This quote from the Ramakrishnan textbook really just nails it. The goal of BCNF is to make sure there's absolutely no redundancy you can find using just those functional dependency rules. It's like the final sweep to make sure everything is perfectly organized.
And believe it or not, we can go even further. The quest for data perfection is a deep one. So let's take a quick peek at the final levels of normalization, which handles some pretty advanced, subtle kinds of data redundancy.
Okay, fourth normal form, or 4NF, is all about what we call multi-valued dependencies. Here's a great example. Imagine you have a table about professors, and in that one table, you're tracking two separate things, the courses they teach and the languages they speak. If a professor teaches, say, 3 different courses and also speaks 2 languages, you might end up creating 6 rows to show every possible combination. But that's wrong. It creates a fake link between a specific course and a specific language. 4NF says, nope, don't do that, split them up. One table for courses taught, another for languages spoken. Keep them separate because they are separate facts.
And finally, we reach the final boss, fifth normal form, or 5NF. This one deals with super rare situations called join dependencies. What it really boils down to is a guarantee. It guarantees that if you break a table down into its absolute smallest, most logical pieces, you can always join them back together perfectly to get what you started with, without accidentally creating any fake data in the process. To be honest, this is more of a theoretical ideal than something you'll do every day.
Okay, so we just went on a pretty intense journey, all the way from 1NF up to 5NF. Now's the time to take a breath and ask the most important question. Why? What was the whole point? Why does any of this actually matter?
The payoff, it turns out, is huge. What we get at the end is a database that's not just efficient, but robust and, most importantly, trustworthy. We've eliminated all that duplicated data, which saves space and, crucially, prevents all those dangerous anomalies we saw at the beginning. You get rock-solid data integrity, and that makes everything else, building your apps, running your reports, so much simpler and more reliable.
But I want to leave you with one last question to chew on. We've spent all this time fighting for the perfectly structured, completely normalized database. But is that always the goal? Sometimes, for pure performance, designers will intentionally de-normalize their data. They'll break the rules we just learned, mushing tables back together just to make a specific query run lightning fast. It's a trade-off, right? Purity versus speed. So the real question for you is, can you think of a time when raw speed might actually be more important than perfect, clean structure?